you may have to do the reading of the lectures before I deliver them and work on the things you read on your own. I mean, like the next lecture is on regression, and a lot of you supposed to have taken this in some other course, right? And the notes will be there, so I will try my best to cover the material before the actual homework is due, but you can imagine if the homework is due on a Friday and I cover the last topic on Thursday, it's not optimal, but really the alternative is to do less and less, and that's not a good option for you. All right, I see the light is on. All right, so what, all right, let's see this thing if it's coming up. So we were talking about hierarchical Bayes, an extremely important topic, was probably the most important topic from all the lectures up to now. And I remind you to reduce the effect of the parameters theta, we introduce another prior on theta that depends on some hyperparameters eta. And so we built it a hierarchical model. And so this table gives you all the possibilities that you have available that we have seen up to now, starting with the maximum likelihood, no hierarchical modeling here. A map estimation where you have some parameters theta in the prior, but you fix them. You put whatever value you think is reasonable, and you compute the thetas that maximize the posterior, this likelihood times the prior. And then what we covered the last lecture was this empirical Bayes formulation, where we computed the marginal likelihood, the way we have seen it for model selection, and then we maximize it with respect to the parameter theta, and we fix those parameters theta when we do prediction. So you can think actually, for example, doing a map estimation where these parameters are not fixed a priori, but they're fixed by maximizing the evidence, okay? And we talked why this is very important. And eventually the most complicated thing, if you want to, is to put a prior on the parameter theta and do a full Bayesian analysis where you calculate the posterior of theta and eta, and then you marginalize eta. All right, so that would be an expensive proposition. So what we did is we already did one example, and I want, we started highlighting this, the hierarchical Bayes formulation for the Gaussian model, so I want to go back to that. So let's remember what this problem is about. We have these schools. In each school, there is J number of students, and we are interested to estimate the mean score of the students in each school for a particular class, let's say. Okay? So theta j is the mean score, let's say, in statistics, and we have d different schools, and each of the schools has its own population. Some schools are small, some are big, and xij is the test score of the student I in the school J. So the unnormalized posterior just looks like that, the standard way. Okay, so as we have this summation, this product outside, but I put it inside for a reason. So we have a product over each of the grades, over all the schools, of the likelihood of xij for school J. You notice here there is a reason I'm keeping the variance to be constant. You can actually modify this and allow variability from school to school. So for example, you can maybe use the empirical mean of each school to define sigma square. But it adds a complexity on what I'm going to try to do in the next few slides. So if sigma square is not the same, whatever you're going to hear is not correct. Okay, it needs, you need to use expectation maximization and don't move like that. That's bad for me. So this is the likelihood, this is the prior, and the hyperparameters of the prior are mu and tau squared, that we call them collectively eta, and we're going to try to compute eta by maximizing the evidence. All right, and I gave you one trick. So when we try to write again the unnormalized posterior, a few things have happened here. This product over for each school, the product over the number of students, and the likelihood of this grades xij, I wrote them collectively as a Gaussian that involves the sample mean with the same mean grade theta j, and a variance sigma j square that is sigma square over nj, just to make life easy and not to read everything that is there. All right? So effectively, this nj Gaussian likelihoods, okay, together, you can combine them as one likelihood of the sample mean, right, that follows a Gaussian distribution with the same mean theta j, but the variance, this is very important, right? You can connect this with the central limit theorem. The variance sigma j is sigma squared over nj. So a nice way to get rid of that product over the students for each school. So what we have really here is we have a product of two Gaussians, and this product is over the number of schools. All right, don't pay attention to what this blue line is, but you will appreciate the fact, right, that if we do empirical Bayes, somehow we're going to maximize the evidence, and we're going to compute some point estimates for the parameters mu and tau. And that's what I have here. And I'm going to explain to you from where these calculations come for this Gaussian model. But right now, just say that somehow we optimize the likelihood, the marginal likelihood, and somehow we computed those two parameters. All right? And this is how now the joint posterior looks like. Okay? So this results is coming on the next slide, so I'm going to give it for you. But what I want you to observe here is that somehow, if I multiply this, and if I expand this Gaussian, and then complete the square, for those who are familiar on this, all right, we're going to get a posterior for theta j that's also Gaussian. Can you see that? You have two Gaussians, right? If you expand them, you know, two squares on theta j minus something and all theta j minus something squared, you will get a Gaussian. And it's going to look precisely for each j. So the posterior really factorizes over the schools, and for each j, the posterior looks exactly like this. There's no miracles here. It's just Gaussian times Gaussian. So if I go to Wikipedia and say product of Gaussians, you can just cut and paste, and this is what you get. Okay? So the posterior comes to have this nice form. So I need to define all the symbols. For right now, you know, treat that mu hat and tau hat square. Somehow we have computed them, and we will see from where they come. But once you have computed them, this too gives you a Gaussian. So that's the posterior of theta j. And the Gaussian has a very nice mean, and then has a variance that looks like this. So let's concentrate on the mean, right? Because at the end of the day, what we're really interested is, you know, to compute a better estimate for theta j than the Mle estimate. So when we look at the posterior mean, okay, it is an average of mu hat and xj bar. So remind me, what is xj bar? The way we define it here, what was xj bar? Louder, you know, people cannot hear you. The empirical mean of the grades for school J. Everybody sees that? All right, so xj bar is what you will expect, actually. Sort of, you know, it's like the Mle estimate, if you like, for school J. So you just collect the grades for school J, and so that's xj bar. And what is, according to the definition here, what is mu bar? So xj bar, you told me, is the empirical mean for school J. So what is mu hat? Is the empirical mean of the empirical means of each school. So this is the pooled mean, right? Putting all the data together and averaging all the means, this is what you get. So can you appreciate now what this posterior mean does? Depending on this value of beta j, is if you don't have sufficient data, all right, or you don't have confidence in your predictions, this is going to pull you in which direction? It will push you towards the direction of this pooled mean. All right? If it happens that beta j is equal to 0, all right, this is not important, and what you get is you get the empirical mean for school J. All right? So this, what you see here, is called the stringent effect. All right? So if you don't have sufficient data in school J, this methodology shrinks you towards, it moves you towards this pool mean mu hat. Okay? And this beta j hat comes to be sigma j squared divided by sigma j squared plus, again, this tau squared that we need to discuss it. In the derivation that I'm going to give you, again, this sigma j squared, I'm going to keep it to be the same for each school, because if it is not, you have to do a modification to the analysis. But so I kept it like that, so at least I emphasize the meaning of this. So sigma j squared is sigma squared over nj, all right? So if sigma j squared is very high, what does that mean? For school J, if sigma j squared is very high, means you are very uncertain, right, for your grades in school J, okay? And if sigma j squared is very high, how much is this ratio? 1, and then you're pulled towards this pool mean. And similarly, if sigma j is very small, right, you're very confident, then this thing becomes 0, and you get basically the Mle estimate for school J. Okay, so this is this is the estimator we care, the posterior mean, because you remember in Bayesian analysis, right? If you want to do a point estimate and you want to plug in an estimate of the parameters, what you plug in is the posterior mean estimate. And the posterior mean estimate, if you want to do it that way, not being fully Bayesian, is this thing that you see up there. Okay? So this is fundamental, not only in the context of one or two examples we have seen, but this comes in many settings in Bayesian analysis. So I want you to remember this type of thing. So somehow we build a model that shares resources, in this case between different schools, to allow us to have a better estimate of the average grades in school J. You don't do this separately for each school, but you put information together so that you can improve your predictions. All right, so how do we get this mu hat and tau hat? The methodology says compute the marginal likelihood and then maximize it with respect to the parameters. So what I have done is, you remember we had the joint, the unnormalized posterior. It was the product of this Gaussian. So to get the marginal likelihood, I have to integrate the parameters out. And again, I'm not going to do the algebra. You can expand the two Gaussians. You can look at Wikipedia. You know, immediately what you get is you get a Gaussian that looks like this. Okay. I don't know if I should put this equal because we don't really care. So this is proportional to that. Okay. So and you remember the posterior and the evidence basically factorized over each school. So the final result looks like that. Okay, so the marginal likelihood, okay, it's a product over each schools of these Gaussians centered around mu, and the variance is sigma j squared plus tau squared. All right, so can you tell me now how I am, so we need to compute mu and tau squared to maximize this evidence. And tell me if this reminds you anything, you know, from earlier courses in statistics. So this looks to me like independent samples from a univariate Gaussian, and somebody tells you, can you find me a point estimate of the mean and the variance? What do you do? What's the easiest thing to do? Huh?
Sample.
You use the sample, basically what's the Mle estimate, right? The Mle estimate comes to be the sample mean or the sample variance. Okay, and that's the answer. That's what I have written here, that mu hat is the sample mean, and the variance is the sample variance, okay? And it's the variance against with respect to the sample mean that you see there. And you notice, to be able to apply this analysis, I really have to treat sigma j squared to be constant. All right, so that's a weak part of this particular analysis. Otherwise, you're going to have to treat things in an iterative fashion using expectation maximization. And this already has been done. Okay, so there is mu hat, there is tau hat, and we're done. Okay, so the estimator looks like this. And if you take all the beta j's to be the same, because sigma j is the same, the estimator looks like this. So this is the pooled mean, x bar, and this is the sample mean for school j. And this formula here that you see is what's called the James-Stein estimator. Has been around basically for, I think at least historically, 30, 40 years. And as I said, this concept of sharing resources and pulling data from an individual source to some pooled source, okay, it's fundamental to Bayesian analysis. So remember, this type of thing is being used for stabilizing point estimates in Bayesian analysis all the ways. And sometimes you may see it with no derivations. So people look at this and say, you know what, I'm going to do something like this, and then they figure out some artificial way what beta is going to be. But in this case, we derived all the quantities because the model is simple, it's Gaussian, and we can do the analysis nicely. So this rank estimate, really what it is some sort of regularization, right? So it tells you, if you don't have sufficient information in one school to make decisions, I will regularize the problem to allow you to make the system. All right, I'm going to only briefly mention the last example, which also related to the Stein estimator. Let me go back to this analysis. You notice here we managed to write the likelihood model as one Gaussian, right? This was the Mle, right? With a true, this is the true mean that we want to compute, and we assume really that sigma j squared is constant, okay, for each school. In particular here, sigma j squared doesn't depend on theta j, okay? So it's a Gaussian, and it is the mean really we're after. So imagine that you have a problem where the likelihood is not a Gaussian, but in this particular case is a binomial distribution. So the example is the following. You have 18 players, and you count the number of hits in baseball, not that I know anything about baseball between us, in 45 games. And the number of hits follows a binomial distribution, I can see that. So this is, in T trials, basically theta j is the average number of hits, and you want to compute an estimate of theta j. So this sounds very much, right? You have different players over the games. You have a nice likelihood model. Sounds exactly like what we did for the Gaussian case. The only difference is the model is not Gaussian, and you cannot do the same analysis. It just doesn't work. So what you're going to do is, so the Mle estimate, by the way, in this case, for the parameters, okay, is the empirical average. So it's the number of hits divided by the number of games for each player. All right. So that's the Mle estimate. And somehow what we would like to do is we would like to go away from a binomial likelihood and use the concept of a Gaussian likelihood. So we would like somehow to approximate this with a Gaussian, okay? And so if xj is the average number of hits per game, so it comes out, if you take the mean of beta j divided by t, this following a binomial, it comes out that xj has a mean actually theta j, which is what we're interested, okay? But unfortunately, when you compute the variance of xj, so if you take the variance of xj, 1 over t squared times the variance of bj, and you take the variance of binomial, it comes out that the variance is a function of the mean that you want to compute. So everything fails, basically. You cannot use this Stein shrinkage estimate, this regularized estimate, even if you do the Gaussian approximation, because in the Gaussian approximation, the variance is a function of theta j. So in this, and a few other problems similar to this, you should not be desperate, right, and say it's hopeless, because there are tricks you can do. And the trick you can do here is apply this equation. Transform this xj to some yj through this weird transformation. What is the objective of transforming in probabilities one variable to another? Here xj, it's a nice Gaussian, has the right mean, but the variance is a function of theta j. So we would like to have a transformation that does what? It still keeps the mean to be the same, that's what we're interested, but somehow having a variance that is independent of theta j, constant in particular. So this transformation is what is called a variance stabilizing transform, and I give you all the derivation in this particular problem, including the definition, all right? So I'm not going to go through this, okay? The only thing I'm going to tell you, if you do this transformation, it comes out that yj is a Gaussian with some mean mu j, all right? And some variance equal to 1. Okay? So the idea now is trivial. We're going to do the Stein estimation. We're going to compute the posterior mean of mu j, all right? Using this regularized estimator. Okay, so this is what we did before. Because this model is Gaussian, all right? I just write directly this, and the equation for beta hat is exactly what I had before. And what do you do once you compute mu j? You don't really care about mu j. What you compute mu j, you have to go back. This is the mu j is the mean of that. You're going to have to go back and compute xj, all right? So from this mean, you're going to compute the posterior mean given by this nice expression, then you're done. Okay? So basically, the stabilizing estimate is not directly for theta j, but to a transformation of theta j. And the transformation is needed because we wanted to make the variance of this in the likelihood independent of the parameter theta j. There are some results in a computer program that maybe you should look as you do the related homework to get an idea what's going on. So what you see here is for the different players on the top are the Mle estimates, and notice the posterior mean estimates, all of them have shrunk. There was not sufficient information, these Mle estimates were not very good estimates, so from all of these Mle estimates you were shrunk to some pooled, if you like, but transformed, as we saw, posterior mean that looks up there. And further, if you try to plot the mean square error defined as such, so the mean square error here is the square error between the true parameters that you compute with lots of data sets and different estimators such as the Mle, this regularized Stein estimate, okay? So if you plug in this, you get estimates here. So this is the true estimate, the true error. This is the shrunk regularized estimate, and the Mle estimate is this red line here. Bottom line is the shrunk estimate gives you predictions that they are very good, okay? And so this is what you need to do, and it's all a result of this hierarchical Bayesian analysis, and typically going with the name hierarchical Bayes. Okay, so what I want you to remember as we finish this lecture is this table. You really need to understand what's available to you, okay? The third line is this approximation. It's not fully Bayesian, so you can be criticized, but that's something everybody does, okay? Everybody does that. You can actually, so you see it here in two hierarchies from theta to eta, you know, but you can actually do this in further hierarchies if your problem requires so. And so the idea here is find eta that maximizes the marginal likelihood, and then you can actually, for that eta, you can use plug-in approximations such as the posterior mean, and these plug-in approximations lead to shrunk estimates that look like this. Okay? We have done this here for the posterior mean, but if you search the literature and you look at other books, you will find these rank estimates in the context of the covariance, for example, of a matrix, you know, for matrix completion problems and things like that. So they very much look almost identical. Okay, so we're done for that. So the next lecture is a little bit elementary, and I was debating if my computer behaves. By the way, the mouse, you see any mouse moving? Yes, is this moving? How come I don't see it? All right, so let me try. Tell me when I reach the corner. There? Okay, so what do I do? Escape, okay, we try escape. Oh, I have an idea. This always works, okay? All right. Come on. I think my computer doesn't like the heat, the cold. What heat? The cold, right? When I arrived with my computer in the office, the temperature of the computer was literally, oh, come on. Okay, now I see something. All right. Introduction, okay. All right, so what I was saying is I was debating if we should do this, but because I decided to at least, whatever chapters we try to cover from Murphy's book, to cover things rather than cherry picking what I like and what I don't like. So this is decision theory is something actually we never teach, students. We don't even do much research about it. But at the end of the day, if you're going to do machine learning and uncertainty quantification and predictive modeling, for what for? And the answer to what for is for making decisions, okay? And if you actually search, I found in somewhere else a whole course on decision theory that is way too, if our course is 700 level or 7,000, then it was like 25,000, because it was all game theoretic for students basically in information science, computer science. But you will find lots of material out there that is very relevant to research today. But what we will do is we will sort of be a little bit basic, and we try to make some connections with things we will start discussing in the context of regression, classification, and surrogate modeling. All right, so let's consider this decision-making as a problem that is sort of game theoretic. So we play a game with nature. So nature picks up some parameter y, okay, that we don't see it. Okay, so nature picks up y that we don't see it. The only thing we see is some observation x. Okay, and somehow we have to take some decision, some action, and you can consider that the action that we have to take is, let's say, trying to guess what y is. But it can be obviously much more complex than guessing y. It can be something that if we knew y, we will drive this way. If we knew y, we will drive that way. All right? But somehow, interpret that we need to make some decision as if we knew y, but we don't know y. The only thing we know is some observation x. So we define this unknown parameter or state, the observation, and then a decision space from where we have to take some action. Now, if you take an action, obviously, this is the concept of a loss function. You're going to basically not be correct, so you're going to incur some loss, okay? And I mean loss here, not just in the mathematical terms, right? But if you take a decision and it's the wrong decision, you're going to have to pay for it. And so we define this loss, L of y, comma A is our action, y is the unknown state that we don't know again, right? So we don't really know why. A is the action we take, so we know that. And we want to pick up A so that we minimize this loss function. All right? So that's the subject, basically, of decision theory, to postulate a loss function and somehow find the means to optimize this loss function and compute what the decision A has to be in order to minimize this loss function. Now, you need to appreciate that you try to minimize a loss function, but you don't really know why. All right? So what exactly do you minimize? So we will have to discuss a little bit about that. By the way, if you try to let your heads run wild here, you may appreciate that some of these ideas are very much also related with the concepts of design of experiments. All right? You say, what should the next experiment be so I can be most informative for the things I want to predict? Okay? And depending on what you do, again, you incur a loss, and there will be unknown things in that loss, but somehow you want to minimize that loss. So let's consider some examples of a loss function. So this is a square quadratic loss function, y minus a squared. And this is a misclassification action. So you can, if y is different from a, all right, means basically you did not select the correct y, so the loss is equal to 1. If y equal to a, all right, then you get a loss of 0. So it's a 0-1 loss. All right, but we said that somehow we don't know why, so being able to minimize a function like this y minus a squared is not going to be helpful because y is not known, okay? So what we're going to do is we're going to try to minimize some expectation of the loss function, all right? And we will see in the context of Bayesian analysis what is an appropriate definition of an expectation. So we're going to select basically, so x is the input, so is the data we collected, that x that I showed you before. So given that x, we're going to make a decision delta of x, and that decision has to be such that we minimize some expected loss. Okay, this is an expected loss. You may see this in some other machine learning books as actually instead of minimizing a loss, maximizing a utility function that is more or less minus the loss function, or a constant minus the loss function. Practically, the two things are identical. So what expectations should we consider in postulating here? And the idea here is, since we're Bayesian, we're going to take the expectation of the loss function with respect to the posterior probability distribution, right? We computed x, which means we should be able, in a Bayesian setting, to compute a probability of P of y given x. We agree? So the expected loss, basically, that we have to minimize is one. We need to take the action that somehow minimizes the posterior expected loss the way that you see it here. Okay? All right. So let's do some examples to see that minimizing this posterior expected loss, it's actually a common sense criterion that will give us results that they are the common sense results. So let's take this 0,1 loss, okay? So if we guess y correctly, all right, the loss is 0. If we don't guess it correctly, the loss is 1. So this is the 0,1 loss. So let's compute the posterior of that loss with respect to the posterior distribution P of y given x. Can I go from this to that? So this is the definition, right? I plug in this. This is the expectation with respect to the posterior distribution of y. Can I do this? Yes? All right, if the answer is yes, this times that will basically give me 1 because this distribution is normalized. And because this is the indicator function, then a will go inside there. So this is 1 minus the probability of y equal to a given x. And you remember, what is the objective here is we want to minimize what? The posterior expected loss, correct? Which is this. To minimize this, what do you need to do? You need to maximize what? So this is your decision rule, okay? From all possible y's, okay, you will pick up the one that maximizes the posterior distribution, okay? All right, so let me do another example, a little bit more elaborate, okay? But it's an important example. So let me define some set of y0, and you can start thinking of this as being, class 1 versus class 2. So this is, let's say, a loss class. So if y belongs, y0 is a reference class, all right? So if y belongs to y0, the loss, I put it 1 minus alpha. Otherwise, I put it equal to alpha. Okay? So if you take the posterior expected loss, you can write this. All right? So this is the posterior probability of y belonging to y0 given x times 1 minus alpha. And then the probability that y doesn't belong to y0 given x. These are posterior probabilities times alpha. And then you can simplify this. All right? If alpha equal to 0, then the result is the probability of y given belonging in y0 given x, which is that. And if alpha equal to 1, then you have, if alpha equal to 1, this is 0, and you have the probability of y not belonging to y0, and it looks like that. So with this definition of the loss function, the posterior expected loss looks like that. So now you're going to have to tell me what action to take. I computed for you the posterior loss, all right? The expected posterior loss. This is the result. Now you have to tell me what action should I take. Should I take the action alpha equal to 0 or alpha equal to 1? I only computed the expectation of the loss function under the posterior distribution, and here's the result. Now what I want you to tell me is, what action should I take and why? Remember, what is the objective in decision making is to minimize what? The loss. So if I pick up, let's say, alpha equal to 0, what do I expect? I expect that this loss that you see here, that it better be what? Less than that loss. You see that? So effectively, if I pick up alpha equal to 0, I better have this posterior probability to be less than that posterior probability, which I can write as 1 minus this posterior probability. So if I take this on the other side, I have the probability of y belonging to y0 given x less than 1/2. So basically my decision rule looks like this. So this belongs to here, right? When I would choose alpha equal to 0 and alpha equal to 1 would be what you see on the top. Look at this and tell me that it makes some sense to you. Think classifying things in class 1 versus class 0, or belonging to this set, or it doesn't belong, you know. So what this thing says, remember our objective is to figure out, all right, what decision to make, with the question in mind being if y belongs to y0 or not, okay? So what does it say here? If I give you an x, where would you assign this? Would you assign it to class 1 or class 0? What this rule says? It says if the posterior probability of belonging to y0 is greater than 1/2, right? Then I will take decision 1. Right? So if you have two classes and the probability of belonging to class 1 is greater than 1/2, then you will assign it to that class. Right? That's what we got here. Okay? So again, we haven't done anything sophisticated. This is just common sense, but we sort of introduce a decision-making formalism by first having a loss function, then taking the loss function, the expectation with respect to the posterior distribution, and then sort of minimizing that loss, and then we have a decision that is given the way that you see on the bottom. So this is a little bit sort of a slightly more sophisticated example. Rather than before we had 1 minus alpha and alpha, right now in the loss function I also have some weights, alpha 0 and alpha 1. So if you repeat the same calculations, basically, the decision is modified, and rather than having 1/2, basically we have alpha 1 divided by alpha 0 plus alpha 1. So if all of these are equal to 1, you get the previous result as well. So this is like a little homework exercise. All right, so let me, again, we haven't done anything about regression, so I would like you to imagine things here, or if you have seen it already, try to get sort of more excited as to what type of things may be possible. So what we do is, let's define. So we take the quadratic loss function, okay, and we will compute the expectation with respect to the posterior of y given x. So I'm expanding this, and I write this as the expectation of y squared given x minus 2 alpha times the expectation of y given x plus alpha squared. So obviously we need to minimize this with respect to the decision alpha. So take derivatives equal to 0. So you're going to get 2 alpha here, and here you're going to get 2 times this expectation. So the optimal decision when you use a quadratic loss function is what? What is the optimal decision when you use a quadratic loss function? What comes to be? What's the name of this? What is z of y given x? What name do it's an expectation? What is that? It's the
Posterior mean.
Posterior mean. So you can appreciate now, there's no map or anything like that. It's the posterior mean that counts. So when you have a quadratic loss function, the optimal decision basically to minimize the expected loss function is really the posterior mean. Okay? Not the map estimate, not the Mle estimate, the posterior mean. So let's imagine how we can actually pull it this prematurely for now in the context of regression problems, right? So let's say you're trying to feed some data with a linear regression model, and the regression function is x transpose w or w transpose x, right? X is the input vector, w are the regression coefficients, so this is your mean response, right? Again, we will see this, we will kill it in detail in one lecture or so, but again, if you had a regression, all right, you will, this will be your mean regression function, all right? And your posterior, so at each location x, you're not going to have a single response y, but you're going to have a distribution, okay, for every x, that in this case is a Gaussian, around this mean with some variance sigma squared. Okay? So, according to this, right, if we extrapolate, we're going to need, so two things. I am writing this for a given x and a given set of parameters w. There were no parameters there, okay? So here I condition, maybe I should put this explicitly, that theta to be a w, all right? So I'm conditioning the parameters w. So this is really the posterior mean that I was talking before, all right? But because w is a random variable, I need to take one more expectation there with respect to what? I mean, when the whole framework says take the posterior mean, right? That's your best decision. So here, this is the posterior mean. So at each location, following this derivation before, this is the best response, is the regression function. But I can take it a little bit further and say, but now, w is a random variable. I'm going to have to plug in there the posterior mean of w. And you know what it comes out? That's basically the optimal decision you can make at every point x if you train the model with data d, is to actually use x transpose times the posterior mean of w. And you know what? This result that you see here, it doesn't really care what distribution, what prior you put on w, if it was a Gaussian, if it was a student t or whatever. This is a very universal result because it comes from this formalism about decision making, all right, where the optimal solution is the posterior mean, all right, and when I wrote the posterior mean here, I was referring to the posterior mean for each point x, but I forgot to account for the fact that in regression we have parameters, so we're going to have to take the posterior mean over those, and it's a plug-in estimate. So at each x given training data d, the best decision to make about your prediction of y is x transpose times the posterior of w. Okay? And again, sort of we highlight it here, right? But this is optimal. All right? We haven't said anything about regression, but if you really want, you say, give me one number, all right, of y, one estimate. So that estimate for this regression problem is x transpose times the posterior mean of w. All right? We don't really this repeat, okay? So if the loss is the absolute loss, can you tell me what is the optimal decision without doing any calculations? Use your imagination now. So if it's quadratic, it's the posterior mean. If it's an absolute value, what is the optimal decision? Again, we collect x, so we have the posterior of y, etc. So we're going to have the posterior loss, expected loss, and minimize it with respect to a. What answer do you think is going to come up if you do the algebra? Huh? Nope. Huh? Nope. All right? So the answer that comes is the posterior median. Okay? And the derivation, the calculation is basically very simple. It requires some tricks, okay? So I have copied the tricks from Robert's book, The Bayesian Choice, that you can actually, the whole book, you can download it freely online from the Notre Dame library. So the derivation is very simple. When you compute the expectation, I have generalized this by putting some weights also, you know. You can make K1 and K2 to be equal. All right, if you actually make K1 and K2 equal, the median would be 50% probability on the left, 50% probability on the right. So there's, again, some integration by parts in the derivation. You should read it, okay? It's extremely informative because this, we're going to spend several lectures to discuss about this type of laws, especially when we discuss regression models that fit under the umbrella of generalization of lasso algorithms. Okay, so, all right. So for this absolute value, the optimal solution is the posterior median. All right, can you guess now? Somebody said the map estimate. When do you get the map estimate? Do you get the map estimate at all? What should be the loss function to get the map estimate? I don't even know if it's on my slides, but you know. So what do you think? Say it again?
Like a delta function or an indicator.
Delta function, I like that delta function. So how are we going to get a delta function there? You know what, I may have to do some jumping, and then on the slide, since I mentioned to you the excitement about come on. I think somewhere in my notes there must be a plot. Now, everybody, since you guys are looking on my slides and don't pay attention to whatever I say, you should at least facilitate me and say, look at slide number, 17, thank you. 17, let me see. No? Good try. Ah, there it is. All right. Okay. All right. So what I have here is, I have a loss function that is y minus x is x, okay, the notation here, this is from Bishop's book, is slightly, so let me explain. So x is what we know, y of x is the decision we made, right? It's a function of x, and t is our target, which we don't know, okay? So, you know, he uses t for the the values of a function he's trying to fit, okay? So we're trying at each x to actually minimize the error between, let's say, the true value, and this is the estimate for a given x, okay? And so the q, already we saw q equal to 2, the quadratic that gives the posterior mean. We saw q equal 1, we get the posterior median. And now, and it says on the bottom, the posterior mode, you get it for q equal to 0. And the answer is, well, and the question is why, as q gets smaller, we're actually getting the posterior mode. So I want you to look exactly what happens as q gets smaller and smaller. This y minus t to the power q will approach 1 on the two sides, and then it will be like a delta function when y equal to t. So if you want, so remember, if you multiply this with the posterior of t given x, all right? So if it is 1 here and 1 there, then the contribution you get from when you evaluate the expectation of that is equal to 1, because the posterior is normalized. The only place where you get something different is in that delta function. So the higher the delta function, the less the loss is. And so remember, this multiplies the posterior. So you want basically to maximize the posterior at this point, right? And that gives you the map estimate. okay, graphically. Okay, so basically, again, the only contribution comes from this dip here. So you want this to be, this dip multiplies the posterior, so you want basically to maximize that. You want to maximize the values the posterior takes on this point, and that leads to the map estimate that we have seen. So when Q goes to 0, effectively you get the map estimate. All right, where did we stop now before? It doesn't matter, so let me go to slide 15. Okay? So, so let me, say a few more things about a very basic regression and models and decision making. And as I said, you don't really need to know any details about regression because we will cover those in follow-up lectures. So what is the idea here is, right? We are given some data, input, output, if you like, all right? So this is input, this is output, and somehow we need to be able at the end of the day, once the model is trained, for every input X, to say something, what is the optimal response, what's the optimal Y of the system, and the notation that Bishop is using is he's using tau for that, okay? So we're gonna use Y of X as the estimate that we get, and tau is the true target, basically, that we would like to get. All right, so there are two steps, as you notice, in being able to make decisions and for each X compute the optimal T. The first step is to do the inference step and compute the joint distribution of the inputs and the responses, okay? And once you have that, then you can start thinking about loss functions, expectations, and maximization with respect to your actions to compute this optimal T. All right, so let me state what we will have is, so for each X, we're going to make a decision Y of X. T is the true target, so we're going to define a loss function. And notice now that I'm going to take the expectation of this with respect to the joint distribution of X and T. Okay? Obviously, I have to take expectations with respect to T because I don't know T. All right? And I have to take also here expectations with respect to X because you know what? I want to do what is called generalization. I want to account for the error everywhere. Not just, let's say, if somebody gives me training data points. I want to be able to generalize the error for all X's, okay? So the expected loss function looks like this, okay? And in particular, if you use a quadratic loss function, the expectation looks like this. So if we already discussed this, if you go and and you ask yourself, what's the optimal Y of X that I can use to minimize this expectation? You can use calculus of variations. Hopefully you learned it somewhere. So if you take derivatives with respect to this function Y of X, if you don't like taking derivatives with respect to the function, just pretend that you take derivatives with respect to what you know. Okay? Hopefully the answer will be the correct one. Okay? So when you do this, simple algebra, and it comes out that the optimal Y for any given location is the expected mean, the posterior mean at that location X. Okay? So that gives you the regression function. So remember this picture because I'm going to use this in one or two lectures when we talk about regression. The idea here is somehow the assumption would be that at each location, there's no perfect value that we're going to fit a function like Y of X of 0, right? There is a distribution, all right? And so that way we account for uncertainties in our predictions. But if you want a point estimate, the best point estimate is this regression function, which is basically the posterior mean of tau given X. There is an alternative derivation that you may want to study, okay? you can actually, so write explicitly with very little algebra, you can write the expectation of the loss function that I had on the previous slide as this term, and this term that does not depend on y at all. So obviously, if you want to minimize this loss function with respect to y, this term here has to be 0. That's what we said before. But just I would like this equation just to remind you that you cannot really bring the loss function to 0. There is an irreducible part of the error that is going to remain there regardless what. And that does not depend on y. Okay? So don't always assume that when you introduce loss functions, somehow you bring the error, the loss to 0. That's not possible. The other thing I'm going to say, since we discussed about these quadratic basis functions, is quadratic, quadratic loss functions penalize basically errors significantly. So if you have an outlier, right? So if at a given x you have a training point that is way out of reality, the loss contribution you're going to get from that point is going to be very significant. And that's why this type of models that unfortunately we use all the time, they are not robust to outliers. Okay? And in that case, you're going to have to go back to L1 loss that I discussed earlier, and those type of things will lead in the context of regression to lasso algorithms. All right, so to get out of regression, here is everything you need to do. You need to take expectations with respect to the joint distribution of x and t, conditional on the regression parameters. So you remember, if you fit things with basis functions, you're going to have some parameters. So thetas are the parameters that you have. This is the generalization error. And really, you're not done yet because theta is a random variable. So you're going to have to find actually the posterior expected loss. You're going to have to take another expectation with respect to the posterior of the parameters given the data. And for a quadratic loss function, the answer comes to be the posterior mean, okay, that we see in this equation. Okay? This is, if you train the model with data D, and you're asking, can you give me one point estimate at x that is the best prediction to the true value t? Well, that answer is the posterior mean. And you notice this posterior distribution gives me the response at x, right? But given the data D. So again, the idea here is the loss function has to be averaged with respect to the joint distribution of x and t. Okay? So again, I remind you, t is not known, so we have to average. X, we integrate over all x's to allow to generalize basically the whole space, right? We don't look at the loss only at one point, but to generalize in the whole space. And then theta is a random variable. These are the parameters in your regression. So you have to take another expectation. So the posterior expected loss looks like that. And the answer is universal. It doesn't really matter what the details are. This is the right answer. So you can go and put complex prior models to this and to that. Whatever you do, if somebody asks you what is the best answer, this is the best answer with the quadratic loss. Okay? All right, so we already discussed this, so we don't want to go back. All right, so let's spend the next 10, 15 minutes to extend these ideas to classification, all right? And in the classification, basically, the idea is we're going to have to make decisions if you give me a point x to tell you to what class it belongs. And the idea here is every decision we take, it will cost us money. So for example, if you go and take a medical exam and the doctor tells you you have this disease and he's wrong, maybe you will get stressed. But if he tells you you are healthy and you have the disease, that's very bad news. So how do we account for the loss function in the context of classification? So the first thing we will do is we will, in the context at least of the lectures today, we're going to use generative models. So we are going to actually start with an inference process where we are going to build the joint distribution of x, comma ck. Ck is a class k, right? X are my data, all right? So I would like to build a joint distribution of x and ck for all k's. And then once I have that distribution, I would like to make decisions when it comes to, for a new x, to figure out to what class it belongs and what the corresponding loss is. All right, so this, it looks slightly strange, but I think it's a very nice visualization of the misclassification error in the context of two classes. So let me try to explain what's going on here. Let's suppose you train a model and you computed the joint distribution of x and sigma 1, which is this bimodal distribution. All right, so this is for class 1. All right, so data in class 1 follow that distribution. All right, similarly, I do this thing for class 2, okay? And I get this unimodal, nice, like Gaussian-looking distribution of P of x and sigma 2. So what we would like is, we would like to make a decision and say, you know what? To the left of this decision boundary, everything is class 1. To the right, everything is class 2. And we would like to figure out where that boundary should be. So I'm starting here. And I say, okay, the boundary, let's say it's here. Everything to the left is going to be class 1. And everything to the right is going to be class 2. Will you agree with me that all these marked color areas are misclassified? Like, you know, if I look on this area and that area, right? It's supposed to be on what class? Class 2, but it's classified to be now class 1 because it's on the left of this decision boundary. Similarly, this, let's say, blue domain here, right? It's supposed to be on class 1, but it's misclassified to be on class 2. How do I write this misclassification, the probability of misclassifying the data? I am writing it like that. So this is the joint probability of x and C2, and I integrate it in R1, which is, it will give me basically those two colors, and then this is the joint probability of x and C1, but I integrate it in R2, and it will give me these misclassified states on the blue color. Can you tell me, looking at this picture, where is the optimal boundary to minimize this misclassification error? Just visually. Where is the optimal boundary that I can move this line so I can minimize the error? And you can see graphically the error is the three colored areas. What is the best place I can put this line? Say it again? X naught. So what happens at x naught? Why is this the best boundary? Which part, you know, which of the colors, the errors from the three colors disappears? What color is this?
Red.
Brown, we said? Red, what?
Red.
It's really red? It's unbelievable. I talking about color blind, okay. So, so this whole thing disappears, okay? So this is the optimal boundary. So can you look now, if that is the optimal boundary, all right, what exactly will be a nice criterion that actually defines that boundary? I mean, we kept moving and we said, you know, the colors, this red disappears, the rest remains as is. But if you look in the context of the two generative models, what is the mathematical definition of this boundary? What happens when you select a boundary to be here? So obviously, you say everything to the left is class 1. So what's the criterion actually that defines that everything to the left is class 1? So if I take a point x, why assign it to class 1 and not to the class 2? Higher what? Higher posterior probability. Because, you know, this is the joint, right? The joint, you can also write it f p of c1 given x times p of x, which is the same for all x's, All right? So the posterior probability of belonging to class sigma 1 here is higher than the probability of belonging to class sigma 2. Okay? And similarly, if you look to the right of X naught, you notice everything is assigned to class 2 because the posterior probability of C2 given X is higher than the probability of C1 given X. The question is there any loss function that actually naturally leads me to this type of result? Is intuition basically something we can prove mathematically? All right? So let me see if it was in the previous slide, maybe not. So there are various ways of doing this, right? So let me, I'm going to write this in the following way. So rather than minimizing the misclassification rate, I'm going to try to maximize the probability of being correct on my assignment. So the way that you see here, I have k different classes, and this is the joint distribution of X and sigma k. So my data come from class k, but I also assign them to region Rk, right? So this is the probability of being correct. Okay? And I split this joint distribution on each region Rk as P of sigma k given X times P of X dx. So what we need to do is we need to find the regions like R1, R2, Rk, so that this probability that you see here, it's maximized. So what is the choice, the best choice for the region Rk? I mean, you look here at the region Rk, you have a summation of all over k's of these terms. P of X, there's no k there, and there's P of sigma k given X. So what do you need to do in the selection of Rk to maximize these terms there? How do you define Rk, right, to maximize the probability of being correct in your assignments? To which class are you going to assign point X? To the one that maximizes the probability P of Ck given X. Okay? All right. So there is a problem with what we have done up to now, right? Is we assume that somehow if you misclassify one way or another, the penalty is the same. All right, you say assign to this class or that, but if you assign to if you take somebody who is sick and you tell him he's healthy, all right, in this case, if somebody has cancer and you tell him has no problem, no health problems, the penalty is huge, okay? So we need to introduce a loss matrix in the assignment of classes, and the way we're gonna do this is we're basically going to rewrite the expected loss that I had before. All right, so you remember we have a joint distribution, all right? We integrate in all of the space X for all classes K, and we split the domain in the regions R1, R2, where we're going to do assignments for different classes. But here we have the weighted loss, if you like, with the joint probability distribution. So effectively what I have here is I have a point X that comes from class Ck, but I assign it in the region J. Okay? So the definition of these regions, the assignments of these regions, has to be such that this loss that you see here for all k's is minimized. I mean, what is different from before, right, is I plugged in this loss function to account how I want to penalize misclassifications, and so the selection of its region is such that this summation here needs to be minimized. Okay? So let me give you one example of this. Let's take this weight there, this loss function, to be 1 minus delta kj. So if I assign data from class K to class K, the loss is 0. If not, the loss is 1. So that's a 0-1 loss. So if you plug in this to this expression to see how it is minimized, you get 1 minus the delta function times P of ck given x. So you have summation of all of this, and you get 1, right? It's normalized. And delta kj ck gives me P of sigma j given x. So if you try to minimize this with this loss matrix, is the same as maximizing what? So remember here, we are in class K and we assign class J. So the class J we're going to assign that minimizes this loss has to be which class? The one that maximizes the posterior distribution, P of Cj. Okay? So again, for this simple loss function, the assignment basically of data from class K to region J with this loss function, right? It has to be such that we maximize the posterior of sigma j given x. Very fast is 145, all right? A lot of times when you make a decision with this posterior probabilities, right? You are not comfortable if, let's say, at 1x, the maximum probability of belonging to one class, let's say, is 0.5, you say that's a very low probability. I cannot accept that. So in that case, what you do is you reject. You say, I am not going to assign this point to any class, and I'm going to take the cost of rejection. Okay? So in this case, you define a threshold theta, and if it happens that all the posterior probabilities for x are less than theta, basically you reject. Okay? And so you can modify these loss functions to include this reject option, and the calculation is actually trivial, and I don't know if this is part of your homework or something else, but we will do this not on Thursday, on Friday, right? As per rules.